In this module, we are going to look at color and light and how to make measurements. One of the things to be aware of is that when we think about the question, what's color? Colors don't exist until we see them. There's no such thing as color without the eyes and the brain. And so the truth is that most other animals and even some humans don't see the reds and orange and yellow and green of the leaves when they look at fall foliage in the forest because their brain just processes visual information differently. So when you look up a definition of color, one of the better definitions that I can find from a book that's called What is Color is that it's a neurological phenomena. And so what we mean by that is it's a perception of the outside world that the human brain creates. In order to create this perception, our brains have to obey the physical laws of the universe, but often in what I would consider counterintuitive ways. Experiences, both collective and individual, play a really big role in the colors we see or that we associate with a given object as well. So color is just really complicated. So even though color vision comes to us effortlessly, it's so complex that neuroscientists who specialize in color vision don't agree on how or why people see color. So color science, and the color science that we're going to talk about in this module and the next module, touches on so many different disciplines, including physics, chemistry, neuroscience, biology, anthropology, linguistics, history, and many more. And we're going to talk about those throughout the course. So a good question to ask yourself would also be then, why do we see color? So, and just an easy kind of answer to this is that color vision helps us distinguish one thing from another to better navigate the world. Additionally, being able to distinguish the color of an object clues us in to the internal state of that object. And so a really good example is here with our tomatoes, right? The color of a tomato tells us if it's ripe. If you have a child that's sick, their flushed skin can tell you if they have a fever or not. Now, while we don't know for certain why humans develop the color vision we have, most scientists studying the matter agree that being able to pick out ripe fruit against a green background is one likely explanation for improved color vision in primates. Most of us, though, are no longer picking our own fruit, but instead, we a lot of times are grabbing our favorite flavor of food or beverage inside the fridge or at the grocery store. And so colored containers make it so that we don't even need to read the label to know that we picked the right soda. And so this is a big trend in marketing. So, if I go to the grocery store and I want Diet Coke, I'm going to look for the silver can instead of the red can. Now, along with shape and texture, movement, darkness or lightness, the more colors we could see, the more information we can interpret in the light-filled world around us. So, for example, if you have two bowls of guacamole that look exactly alike, except for one is bright green and the other is brown, which would you choose? Thanks to your color vision, all right, you can save yourself from having a really nauseating night or an unappetizing experience. Now, color vision is also tied to survival. Today, it's just not about accidentally eating a poisonous berry. It can be like avoiding hazards, like taking the wrong medication. So a lot of our medications are color coded, and colors of bottles, tops, labels, and even the pills themselves help distinguish between the medications. Color is also used to speed up comprehension, right? So, for example, in maps, if you want to go somewhere in Washington, D.C., you're going to go on the blue line, which helps us figure out where we're going faster. So, color vision can help us distinguish one thing from another to better navigate the world. We can see this as far as safety, right? So we talked about pills and guacamole. It also is used to speed up comprehension. And so these are a few of the reasons that we see color. Now, here's the tricky thing. Without light, there is no color. But the relationship between light and color is often kind of baffling and counterintuitive. So light is a physical entity in our universe. Okay? Color is constructed by a brain, right? And the colors that are actually perceived depends on whose brain is constructing them. Right? Now our visual system, well, let me back up and talk about human brains for a second. So human brains perceive just really a narrow band of light, and yet more of us are able to construct a world that's really abundant in color. Our visual system relies on the physical properties of light and the molecular properties of objects that we see to create our color sense. And we're going to talk about that through the class. We're going to talk about the physical properties of light, and that's mostly going to be here in Module 2 and 3. But then we're also going to talk about some molecular properties, and those will fall into later chapters as well. Now, for most of human existence, the sun has been the source of light that makes our world really colorful. Though we humans generally perceive sunlight to be white or golden, it's actually made up of all the colors we see in the rainbow. Right? And these colors that are contained within sunlight are really what enable us to see color in tangible things. Okay. So one of the things that we'll see throughout history is that there has been a really kind of obsession with light. When you look at different cultures, you are going to see that they're ancient sun god tributes. And so if you are really interested in this, I have a website here that you can go to. When you go to this website, it's going to list all of the ancient gods that were dedicated to the sun, right? The deities of the sun. And this is anything from Ra that was in is an ancient Egyptian god, to the Norse sun goddess, to the Hittite mythology and the sun goddess there. So there's just lots of ancient religions that kind of had a sun deity. Okay. And so we traveled from kind of worshiping the sun historically into scientists wondering what was light. Okay. And so one of the things that kind of was thrown around was Plato, which was a Greek philosopher, and I have a bust here of Plato. He lived from 1427 to 347 BC, right? And he thought that vision was possible because, or thanks to, light rays emitted, which would be helpful if I could spell emitted. Hold on. From the eyes. Okay, so that's what Plato kind of thought. There was a problem with this philosophy, which was, why can't we see in the dark? Okay. And so that kind of idea was thrown around, but there was a problem. One of the things that you're also going to see is that light is a symbol of great development or knowledge. So light was used throughout, in the 18th century Europe, when scientific discoveries were made, the overall movement was called enlightenment, right? And so light is also a symbol of knowledge. So for us now, where does light come from? Well, there are two kind of sources that we're going to break this up into, is that we can have luminous objects, and luminous objects emit light from within, right? And here's some examples. So examples would be like the sun, right? Or a star, or a flame, right? Then you could have illuminated objects, and these guys reflect externally supplied light. And this would be things like the moon, right? And so that would be some things that we would see there. Now, so how do we know that sunlight is made up of many colors? The complex kind of makeup of white light was first studied by Isaac Newton. Right. And so what he did is he made a hole in a wood shutter for a beam of sunlight to pass through. Right. And so this is an artist renditioning. So here's his shutter. He made a hole, white sunlight passes through. And then he set up a prism, and he saw that the prism broke the white light into a rainbow. And so his conclusion was that white light isn't white after all. So Newton realized that each of these colors needed to have individual properties, because in addition to their color differences, they exited the prism at different angles. So, right, each of these colors must have individual properties, because in addition to having different colors, they exited the prism at different angles. Okay, and so because they exited the prism at different angles, he said, okay, they're going to have different properties. Now, as we continue on historically, kind of in this idea, right? There were two thoughts here in the beginning of the 19th century. Okay, so there was this thought in the 19th century, right, that particles have mass and you can identify their position. And then there are these things called waves, right? And these are massless, so they don't have a mass, and their position in space can't be known. Okay. And so when we talk about what is light, okay, we know some things about electrons. So electrons are located outside the nucleus of an atom. We talked about that in the previous module. And I'm going to represent electrons with an E minus. So we know that electrons occupy a specific orbit or stare around the nucleus. Okay, and so what happens is when electrons fall from one orbit to another, light is released. Okay, now, so maybe the question is like, how does an electron jump up a stair? Right? Electrons move when energy is injected into the atom. Okay, now this can happen when they collide with other atoms. Or they run into an electromagnetic wave. Okay, so there's a couple ways that this can happen. All right, now when electrons fall down, say when an electron falls down to its original orbit, the energy released is a packet of light called a photon. Now, this is a big deal, okay? Because basically, when you have a photon, these guys have no mass and no charge, right? And when they travel, they act like a wave. Right? Now, a photon sometimes is called a quanta. Okay. Now, here's the deal. These guys can also act like a particle, right? Because we can identify their position in space. So in the early 19th century, or 1940s, 1950s, this really, how we thought about light really got redefined, because when we think about E equals mc squared, which is Einstein's equation, what he's doing here is he's saying, look, energy, right, which we know acts like a wave, can be related, and here's the speed of light, and then now it's got a mass. So all of a sudden now, way back up here, when we talked about the 19th century where particles and waves were really different, now here in I guess it was the 20th century, the 1940s, 1950s, we can relate this light with mass and energy. And so now these two ideas overlap into what we really sum up as wave-particle duality, which is also sometimes called the dual nature of light, where it acts both like a wave and a particle. And that really kind of rocked the world there in the 1940s, right? That's a really big deal. So let's go on kind of and think a little bit more about light and how it relates to color. Now, Newton separated the colored light that he saw exit the prism into 7 colors, which we know by the kind of mnemonic Roy G. Biv, right? We've got red, orange, yellow, green, blue, indigo, and violet. Now, there are 7 colors here. Now, these aren't the actual colors of the rainbow, but they're a series of artificial categories. Developed by Newton. And there's 2 theories I've read here about why he chose 7. All right. And so one of the theories is because he was very religious, and at the time when he was reading the Bible, God created the world in 7 days. And so some of my color books talk about that. So that's one theory. The second theory is because he wanted the visible spectrum to parallel the number of notes in the musical scale. So the number of notes in the musical scale, which is 7. In some sources, and most current sources now, most have removed indigo. But we're still going to see it pop up, but we're starting to see more sources that have really stepped back and said, look, we're going to remove indigo. Okay. So at the turn of the 19th century, another English scientist was able to demonstrate what other scientists has hypothesized. And this English scientist's name was Thomas Young. Right? And he demonstrated that light, right, is a wave, right? And then he also demonstrated that the color of light is determined by its wavelength or frequency, right? Now, a few things to note here, right? The wavelength varies inversely with frequency, Okay. And a color is typically only referred to by its wavelength. Now, for us to talk about this, we need to know a few things about waves, okay? And so a few things to know about this is when we talk about photons, a bunch of photons of light, right, is called electromagnetic radiation. Which we abbreviate as EMR. Okay, and so you're going to see that abbreviation, right? And EMR moves as waves through space at the speed of light. Now, when we talk about waves, they have three characteristics, right? And the first characteristic is wavelength. And when we talk about wavelength, it is represented with a lambda, and it's shown here, and it's measured from crest to crest, and it's just the length of the wave. Now, the unit that we measure this in, anytime we have a number, we're also going to have a unit. That unit is nanometers, and we're going to talk more about that unit towards the end of the middle of this module, okay? Then the second thing we have is frequency, right? And frequency is the number of waves per second that pass a point, right? And this unit is going to be in waves per second, or 1/seconds, or hertz, okay? And that's hertz like that, and there's hertz, okay? And then the third thing that we're interested in is speed, right? And the speed of light is c, that's what it represents as, and it's 3 × 10⁸ meters per second. Now, there's no need to memorize what c is there. I will give that to you, okay? So, right, Thomas Young demonstrated that light is a wave, and the color of a light wave is determined by its wavelength or frequency. So, when we look at this, right, here is the visible spectrum again. Here is wavelength, and here is frequency, what we just talked about. The range of light from red to violet in a rainbow that we see there is referred to as the visible region or the visible spectrum. So these are the ranges from about 400 nanometers to, some sources say 750, some say 800 nanometers, right? So that we can see, okay? And so that's our visible spectrum. Now, visible spectrum is a tiny portion of something much larger, which is the electromagnetic spectrum. Right? And so I'm showing you the electromagnetic spectrum here. The only reason we really this is really called our visible region is because our particular anatomy is responsive to these particular wavelengths. Now, let's look at some other wavelengths here. You're going to see that wavelength increases, right? So we have long wavelengths over here. And we have short wavelengths over here, right? And then you can see the frequency here where this is low frequency and this is high frequency. And so when we say something's inversely proportional, as one goes up, the other goes down. Okay. And so here we have ultraviolet radiation, X-rays like you would get at the dentist, gamma rays, which we would consider radioactive. If you follow pop culture, the Hulk, right, experienced gamma rays. And then here we have infrared, we have microwaves, like what's in your actual microwave, and then radio frequencies. Now, I want us to really take note that when we talk about the visible region, this is what we see as humans. We are not the species that can see in the widest range. And so if you don't look ahead in your notes, I would have you guess, but the species that can see the widest range is the mantis shrimp, right? And so the mantis shrimp has really extraordinary eyes. They can see, of all the animals that we know so far, they have the greatest spectral sensitivity. They can see into ranges that we can't. Now, I'm gonna put up a really interesting podcast. It's by Radio Lab, which is out of NPR, and they're a science podcast. And they do a really great podcast on color. And they did this circa about 2012. And then they updated it a few years ago. And so in 2012, they came out and they were like, look, the mantis shrimp, it's the best, right? Kind of based on this 1999 information in 2007. But what's really interesting is since then, there have been more studies that come out. And what the studies have shown is that the mantis shrimp can't blend color. So when we look, we have three kind of colors here that we see, right? We've got the red and the green and the blue, but we see so many others because we can blend these two together. And it can help us distinguish between things like light blue and dark blue. Well, the mantis shrimp doesn't have that ability. So it either sees blue or nothing, right? It either sees red or nothing. It has what we consider discrete, visual capabilities. And so that's kind of something that is a little interesting. Now, so back to our energy and color talk here. So how is energy related to color? Visible light right? Like all parts of the electromagnetic spectrum is a form of energy, right? And each color we see is associated with a different energy level, with higher frequencies of light having higher energy levels, okay? Blue and violet have the highest energy level and red is the lowest, right? Now, waves of light, like all waves, transfer energy from one place to another. Right? And this transfer is responsible for the colors we see all around us, right? So when light hits the surface of an object, some of the light's absorbed, and some is reflected. Now, the energy of the light that's absorbed goes into increasing the temperature of the object. And I'm going to abbreviate temperature with a T there. And the energy that's reflected is what we see as color. Okay. Now, which wavelengths that are reflected is determined by the molecular structure of the surface of the object. So the wavelengths that are reflected, let me just start over with that word so it just looks better, are determined by the molecular structure of the surface of the object. Right? So think about the sun beaming down on a blue car. Okay? Part of the energy contained in the light hitting the car will heat up the car, and part of the energy will be reflected from it in the form of light that we perceive as blue. Specifically, the medium and longer wavelengths of visible light that do not appear blue will be absorbed by the surface of the car, and the shorter wavelengths of visible light that do not appear blue will be reflected. Okay? Now, we can calculate this energy. Okay? And when we calculate this energy, E represents energy, and that equals H times the frequency. That's new there. That kind of wavy letter there is the frequency. Right? And then this H here is Planck's constant. And I'll give you Planck's constant. Okay? And so because we already know, or well, we can talk about this, frequency equals the speed of light over the wavelength. Okay, so frequency equals the speed of light over the wavelength. We can take the speed of light divided by the wavelength and shove it in for frequency here. So then we can also say that energy equals Planck's constant times the speed of light over the wavelength. And we can calculate the energy of different colors of light. And we are going to do that in the next screencast.